I'm good. How about you?
Good. So what are we going to do tonight?
Log.
Okay. You got specific problems?
Yeah.
Okay.
10 to the x power equals 3.91.
I'm sorry, I'm having a hard time making out what you're saying. Hold on, let me turn my volume up a little bit. That should help a little. What did you say?
Equals 3.91.
Okay. Like that?
Yeah.
Okay. How are we going to solve this? How do you solve this is an exponential equation. And the reason it is because your variable is in the exponent. It's not on the regular line. And we don't have algebra to solve this. There's no algebra that you can solve for x. There's only logarithms. So what should my next step be?
Would it be to add an e or do natural log?
We could take the common log or the natural log of both sides. With this particular problem, there's an advantage of taking the common log of both sides. And that is that if I take the common log, which is base 10, of 10 to the x, this becomes x. And I have to, of course, take the common log of the right side also. But just like algebra equations, you can take the log of both sides. And there's your answer. You can get that number out of a calculator. In other words, your calculator only has two keys on it. It has common log and it has natural log. And so whenever you have a log that's a base other than 10, it presents a few difficulties. You have to do some conversion. But as long as you can work in base 10 or base e, which is what natural log is, then you can get the solution. Now, let's say I wanted to take the natural log of both sides. Okay, now I can take x, bring it down on the equation line, and I get this. Now I can divide both sides by a natural log of 10, and I get that. And that's also an answer. That is going to be the same thing as the common log of 3.91. But it's only because this had a base of 10 that we could do that. Typically, I solve most all exponential problems by taking the natural log of both sides. But this is a particular problem where it's actually easier if you take the common log of both sides. Only because the left side reduces to x immediately if I take the common log of it. All right, what else you got?
E to the x equals 5.7.
What's this? 3 to the x?
E.
E to the x. Okay. What would be a good log to take both sides of this one?
Natural log?
Yeah, because if you take the natural log of the left, that also reduces immediately to x, because the natural log of e is 1. In other words, I can move the x down on the fraction or the equation line, and then I have x times natural log of e, but natural log of e is 1, So as long as this base is the same as that, then it's always equal to whatever the exponent is. So again, I have x equals the natural log of 5.7, and that's also a number you can get out of your calculator. Or do they want you to leave that as the answer?
They want both.
Oh, okay. This is actually the more precise answer, rather than getting a decimal answer out of your calculator and having to round it off. What else?
5 to the x equals 17.
5 to the x equals what?
17.
Okay. What log should I use here?
Log base 5.
You could do that. It's actually not any quicker to do that, and I'll show you why. If I take log base 5 of both sides, it certainly reduces the left side immediately to x, but then I've got this thing that I can't get out of my calculator without using change of base. So what's the change of base formula? How would I get this number from my calculator?
Log 17 divided by log 5.
Right, okay, so those steps we had to take. Now let's go back and do the problem by taking the natural log of both sides. Okay, well, the next step is x natural log of 5 equals natural log of 17. The last step is x equals natural log of 17 divided by natural log of 5. Same number of steps, and I get the same answer. Now, notice one thing. That ratio is the same as that ratio, even though they're different bases. And in fact, it's the same as this ratio, log base 99 of 17 divided by log base 99 of 5. In other words, when you're talking ratios with logs, it doesn't matter what base. The ratios are all identical. And for that reason, the way I'm inclined to do all exponential problems is just to take the natural log of both sides. Always, no matter what the base is. Because unless it's base 10, that's the only time that it's quicker to take a different base log of both sides. Otherwise, it's the same number of steps and you don't have to worry about which base to use. You always use natural log. But it's half a dozen and 1/6 of the other. There's nothing wrong with taking log base 5 of both sides. And if that's what your teacher recommends on this problem, that's fine. Or if that's the way she solves it or he solves it, that's fine. There's always many ways to do math problems. What else you got?
3e to 5x equals 1,977.
1,000 what?
977.
Is it 3e in parentheses or just 3e to the 5x?
3e to the 5x.
Like I've written it?
Yeah.
Before we can use logs here, we want to try to isolate as little as we can. So I want to try to isolate e to the 5x before I bother taking logs of both sides. So what's the very first step I can take that simplifies this thing?
Divide by 3 on both sides.
Okay, what is that number divided by 3?
659.
659?
Yeah.
Okay, next step,
Take the natural log.
both sides. What's the left side become?
5x.
So the answer is okay. Is this fine for stopping and going to the next? I mean, you know how to do that in your calculator, right?
Yeah.
Okay. Incidentally,
So
you use a TI-84?
Yeah.
Have I showed you this program that I found online?
Yeah.
Yeah, it's a virtual one. It's pretty cool. Although I did discover the other day that it's not quite as perfect as it needs to be. All right, what else you got?
E to the 5x minus 3.
5x minus 3? Okay.
Minus 2 equals 10,476.
10,406?
76.
476. Okay. That's the first thing I need to do.
Add 2 on both sides.
Next thing.
Take the natural log.
Okay. So what's the next line that I'm going to write?
Natural log.
Well, I can do that. I can just do it like that. And now what's the next line I'm going to write?
E 5x minus 3.
In other words, what is that equal to?
Oh, 5x minus 3.
Right. So at this point, this is what we have. Now what?
Add 3 on both sides.
Add 3 and then divide by 5, right?
Yeah.
So x is going to be, I can't add 3 to that because I'm taking the natural log of that number. So it's the natural log of that number plus 3. And then I have to divide both terms by 5. I could just put a 5 under it like that, I suppose. Or I could just divide both terms by 5. Either way is correct and just as accurate. Again, you can get these numbers out of your calculator.
Uh, 7 to x plus 2 equals 410.
Okay? How do you want to solve this?
Take the log base of 7.
Okay? What's the left side become?
Log base 7, 410. Wait,
What's the next
x
line?
plus 2. X plus 2.
Okay. In other words, the left side becomes x plus 2. The right side becomes that. Now what?
X equals log base 7, 410 minus 2.
Next line. Because that's not a number you can get out of your calculator.
log 410 divided by log 7 minus 2.
Like that. Okay. And what base is this log?
Which one?
What base? Is that common log?
Yeah.
Turns out that it doesn't matter. It can be natural log, it can be common log, it could even be log base 17, but you wouldn't be able to get that number out of your calculator. So you want to make it either natural log or common log, which are the two keys your calculator has. Okay? Let me give you a problem that illustrates something. You're going to solve this. Notice the problem with taking the log base 7 of both sides. Also, the problem of taking the log base 5 of both sides. You end up with different base logs. So when I encounter a problem like this, I don't take the log base 7. I'm just going to take the natural log of both sides. Okay? Now I can bring that x down, put it there. I can bring this exponent down, put it there. And now I can proceed to solve this equation. Notice that all I have is an equation with one variable in it and a bunch of numbers. So I can definitely solve that for x. It's not trivial, but I can still do it. And I would not be able to do that if I started out. In other words, that's why I tend to always take the natural log of both sides when I'm solving exponential equations, is because when you run into a problem like this, it's much easier than trying to figure out, well, which log base should I use? All right, what else do you have?
4 to 3x minus 1 equals 5 to x plus 2.
Oh, see, I was one step ahead of you, huh? What's the exponent? X plus 3?
X plus 2.
X plus 2?
Mm-hmm.
It's amazing how close I was. So how are you going to solve this?
Natural log of this.
Well, that's what I do. Let's see what happens. This gets a little tricky. Read the next line to me.
3x minus 1 natural log 4 equals x plus 2 natural log 5.
What's next? Think of these natural logs as numbers. That's what they are. They're not variables. Natural log of 4 is a certain number, so is the natural log of 5. So if I were to replace this with a 17 and this with a 19, what would your next step be? Distribute them. Right? In other words, if I gave you an equation like this, 3x minus 1 times 2 is equal to x plus 2 times 3, your next step would be to distribute them, gather all the like terms together on one side, all the numbers on the other, right?
Yeah.
That's what we're going to do here. So let's distribute.
3 has 3x natural log 4. And
Okay. On the right side?
Natural log x natural log 5 plus 2 natural log 5.
Again, this is just a number, that's just a number, that's a number, and that's a number. So if we now have an algebraic equation to solve, and the way to solve them is to gather all of our like terms together. So what's the next step in solving this algebra problem?
Subtract add like terms.
Yeah, so let's take this x natural log of 5, subtract it from both sides. That's going to give me 3x natural log of 4 minus x natural log of 5. And let's take this number and put it on the other side. So now we have 2 natural log of 5 plus natural log of 4. Are you with me? In other words, what we've done is put everything that has an x in it on the left side and everything that has just numbers on the right side. Now this is the next key step. How do I solve for x? What do I have to do?
3 on one side.
Well, let's factor it out. In other words, I want my final answer to be x equals something, right? Okay. Well, I don't know what 3x times that minus x times that is as a number. I could convert those all to decimal approximations at this point and come up with a net x. But the better way to do this, to come up with an absolutely precise answer, is let's factor out the x. Okay, what's left behind?
3 natural log 4 minus natural log 5.
That is just a number. Let's divide both sides by it. Now we have our answer. X equals that. And notice that that's the only real way to do this problem properly. In other words, I have a perfectly precise answer over here. Whereas, if I didn't factor that x out, if I actually converted that to a decimal and that to a number and all of that, I would end up with an approximate answer. If you're taking a math test on this, this is the answer they should have as a multiple choice answer if you were looking for one. And this actually can be changed a little bit. You can simplify that answer. How? Other than converting it to numbers, which I can certainly do. I'm not sure there's a need to simplify this. I'm not sure if your teacher would want you to simplify this. But notice that the 2 becomes an exponent. So that's actually the natural log of 25 plus the natural log of 4 all over the natural log of 4 to the 3rd power, which is 64, minus the natural log of 5. Now I can actually turn that into natural log of 100. Right? Natural log of A plus natural log of B is equal to the natural log of A times B. And in the bottom, because I am subtracting, that's the same as the natural log of 64 divided by 5. Now, that's as far as I can simplify it. Notice that I cannot apply my log rules anymore. It only turns into division if you start with subtraction. If I start with natural log of 64 minus natural log of 5, then I can turn that into a quotient, a single natural log of 64 divided by 5. When I have natural log of some number divided by natural log of some different number, I can't simplify that. It's as good as I can get. Actually, probably could simplify that the more I think about it. Just not sure to what. I'm not sure I can simplify that. But you can't, it's real easy to confuse the rules of logs when you come across this. Because it looks like the rules of logs should apply. We got two logs and there's division going on. But that's not where you can compress it. You have to have logs with addition or subtraction or exponentiation going on before you can compress or expand. Alright, unfortunately I have a 7:30, so I only have 4 minutes, but we got time to do one more probably.
E to 2x minus 2e to x, no, just x, minus 3 equals 0.
All right. What we are looking at here is a quadratic in E. In other words, we're used to quadratics looking like this. Right? If I gave you this problem, you'd merely factor it into x minus 3 times x plus 1 and solve it that way. Correct?
Yeah.
Well, notice that this is a quadratic because the first term is the square of the middle term. If you square e to the x, you get e to the 2x. So I can use a technique called substitution if it makes you feel better or if it's easier to see, where I'm going to let z equal e to the x. Okay? It's a technique that you could say is substitution. So this quadratic becomes z squared minus 2z minus 3 equals 0. Factor it to z minus 3 times z plus 1 equals 0, and I have z equals either 3 or z equals minus 1. Now I go back up, resubstitute, so I've got two equations to solve, either e to the x equals 3 or e to the x equals minus 1. Those are the two equations to solve. Which one of those is impossible? The bottom one. You cannot take a positive number and raise it to an exponent and get a negative number. So this e to the x equal minus 1, that's an extraneous solution. The only problem I have to solve is that, and you know how to do that. In other words, x is going to be the natural log of 3. That's your final answer. X is going to be the natural log of 3. If you solve that part there. Now, did I need to use substitution? Not really. If I don't have to use it, I can factor this just as easily without using substitution as long as I recognize that it is a quadratic in E. If I know that it is a quadratic in e, then that has to be e to the x. This has to be e to the x minus 3 plus 1. And that gives you that quadratic. So now I go through the exact same procedure, only it's a little more efficient without using substitution. Here's my two solutions. This is clearly impossible. Solve that and you're done. So the real key to this problem is recognizing that it is a quadratic. You can have quadratics in a lot of different things. You can have quadratics in x. You can have quadratics in e to the x. You can have quadratics in sine x. So that you would have, say, sine squared of x plus sine x, or minus 3 equals 0, and that would be a quadratic in sine x. It's a little harder to recognize that that's a quadratic, merely because it's not completely obvious that this term is this term squared, but it is. It's not that whole term squared, but it's the middle term squared, and that's what you need for something to be a quadratic. All right. Mina, are we still going to keep the Tuesday appointment on the books? Tuesday and Thursday at 7?
Yeah.
Sounds good. I'll talk to you next Tuesday.
Okay. Bye. Thank you.
Bye-bye.